So without further delay, here's Bill Berquist to provide some background and assistance with testing and documentation of RTDs, thermocouples, and thermowells.
Well, good afternoon, everybody. Got the session organized today in a couple of different sections here. First, we'll talk about the temperature probes and then move into thermowells. The first thing I'm going to do is cover some of the standards and specifications that drive some of the documentation that is generated for RTDs, thermocouples, and thermowells. And then we'll look at the some samples of those documents. And first off, we'll start out with just a little bit of history of the RTD. It was first patented back in 1922, and it really hasn't changed a whole lot since then. It's in its most basic form. It's platinum wire wrapped around a mandrel and has a 3 or a 4 wire circuit connected to it to eliminate the lead wire resistance. A couple of standards that define the resistance versus temperature relationship. The international standard is the 60751. Previous to that, it was this DIN 43760. And what these standards do is it looks at this resistance versus temperature relationship, and then it assigns what we call an interchangeability or a tolerance class to that relationship. In the U.S. here, there's an ASTM standard. It does the same thing with slightly tighter tolerances. And if we look at these interchangeability levels with some equations here, we can see if we were, as an example, if we were looking at an ASTM standard and we wanted to calculate the interchangeability or this manufacturer tolerance at a given temperature, we just plug that temperature into this equation. If it's a below 0 temperature, you drop the negative sign and run through this, and it'll give you this plus or minus tolerance at that temperature. You can also look at this graphically, and you can see pretty easily the difference here between the two standards. The IEC has a little wider tolerance band than the ASTM does. And down here at 0 degrees C, the manufacturers adjust the sensors or the actual sensing element as close as they can get it to 100 ohms. And these lines are the tolerance bands because unfortunately we can't do it to exactly 100 ohms. There's always a little tolerance band associated with that. One of the ways that we can eliminate that tolerance band, or most of it anyway, would be to calibrate the RTD and match it to a transmitter or some other readout device. And this will generate a document that would define what was done. If we look at matching this specifically to a transmitter, we'll take and calibrate the probe. So we compare the temperature probe to a known standard. We generate the resistance versus temperature table and the calibration coefficients. And these coefficients are used in an interpolation equation, which in some transmitters have this capability when you input those coefficients, they have all the math and stuff built in, and so it can actually interpolate between the actual calibration points and give you a much more accurate temperature measurement than you can by using just a probe that has not been calibrated. And then you'd have to look at those interchangeability numbers as essentially your accuracy of the probe at those temperatures. Doing this eliminates all that. So if we look at the like a sample certification for that, this would have some information about the probe and the order, and then farther down on this particular report there is the actual calibration data. And this one was calibrated -38 to 200 degrees C. These were the actual resistance numbers and the transmitter output. If we look here, we have the resistance at 0 degrees C. So as we can see, this one was just a little slightly lower than the 100 ohm nominal. Calculated these calendar Van Dusen coefficients, and these are the numbers that would be entered into the transmitter and giving it the information it needs to look at the actual resistance versus temperature characteristics of that probe. Some of the transmitters that don't have the interpolation equations in their software, you can also use this calibration information to set just a simple zero and span. This transmitter, for example, is analog, and it has these little potentiometers in it where you can adjust it to a given milliamp output with known resistance input from the temperature probe. In addition to this calendar Van Dusen or CVD equation, there's an improved version that was done in 1990. The advent of a little more computing power made it possible to get a better interpolation of the resistance versus temperature characteristics between the actual calibration points. It's mostly used for laboratory standards, not so much in the industrial grade. Most of the transmitters and things and other equipment will have the capability of doing this calendar Van Dusen interpolation. The higher end readouts and other devices for doing a calibration will be able to do it with this ITS 90 coefficients. And now the labs that are doing this, some will be accredited to some standards. This ISO standard is one of the most common, and then there's an ANSI NCSL Z540, and they'll be done to an accredited lab. A couple examples there would be this NVLAP, which is the National Voluntary Laboratory Accreditation Program, which is part of NIST, and then A2LA is another fairly common one. Now these labs will be able to say that, okay, whatever calibration we do is traceable back to some standard. And a typical calibration certificate that you would get from a lab like this, let's see. I think maybe we forgot to load this one up, unfortunately. Yeah, I don't see it in the list here, Jeff, so I guess we'll have to skip that one somehow unless you can magically make it appear. So.
Let me see if I can make it loaded up if you want to.
I'll just keep going.
If you just want to entertain. Actually, you know, this is a good point. While I try to do that, we're just going to open up a quick little poll here on calibration, and really kind of just ask you a couple questions about your calibration needs. And so, why don't we take a couple seconds, go ahead and answer those questions, and we'll see if we can't find the document we're looking for here. This one? I'll let you do it. I don't know what you're Okay, well, luckily we were able to find the document we're looking for, so I'm going to go ahead and the poll is closing out right now. So if you want to go ahead and submit your final answers, you got a few seconds and it will close. But it looks like so far, looking at some of the numbers, and I'll share them as soon as the poll closes out here. Okay, so it looks like about 44%, so almost half need calibration certificates all the time, and it looks like the vast majority are looking at a multi-point calibration as opposed to just an R0 point. So good information. So, all right, Bill, if you want to go ahead with your calibration cert.
So we'll get this pulled up here. And I just wanted to show some of the information that's on a typical calibration cert. Here, this one is accredited by NavLab, and you'll see down here just barely, if you kind of squint a little bit, that there's a lab code associated with that. So you could actually go look up their scope of accreditation on the NIST website and look at all the uncertainties and how that's all done. Up at the top on this form, there's just some kind of basic information about the probe, how the calibration was done. This says it was comparison to an SPRT, which is a standard platinum resistance thermometer. The temperature range, and then there's some information down here about how the uncertainties were calculated. And then we have the as found information. This particular one, it shows that this 0 degree C point, the uncertainty was 25 millikelvins and was done from minus 196, which is liquid nitrogen, up to about 420 degrees C, and all the associated uncertainties that go with it. And here, since this is a secondary laboratory standard, we have the ITS 90 calibration coefficients, and these would be entered into some sort of readout device, most likely, helping that device interpolate between these calibration points so that it displays a correct temperature. Then down the bottom of the form, it'll list the equipment used, who did the calibration, and a lot of these will have, in addition to this, some manufacturers publish a resistance versus temperature table, which has, it could be in 1 degree C increments, or I've even seen them in 1/10 degree increments of the temperature resistance relationship. Some of the other documents that go with RTDs, industrial RTDs anyway, and thermocouples would be the certificate of conformance. And this is just going to say that the manufacturer built the parts and tested them per the requirements of the purchase order. I think there's a statement down the bottom here that says that. It says who prepared the report. Sometimes there's tag numbers associated with it, so it just provides another level of kind of checks and balances that the probe has been built, calibrated, whatever, per what the purchase order states or any applicable manufacturer documents. Some of the other documentation is actually labeled right on the part. A good example of this is all these hazardous location approvals, either from like Factory Mutual or Canadian Standards, UL. In addition to the label on the part, there may be a diagram or a drawing that shows how the component is connected. Sometimes the conduit openings needed to be plugged, or some various other information is available. So you may see the label on the part, plus you may get a document also that has that sort of information on it. And CE marking, in some cases we've seen where CE marked temperature probe is necessary. Most of the time, however, the temperature probe is part of a larger system. It may be attached to a transmitter, or it may be installed inside of a larger system that carries the CE marking, and so the individual components don't actually need to have that. But in some situations, the actual temperature probe will be marked with CE, and it's purely it's a European-driven requirement, and it just says that it's been tested or evaluated against some directives that are out there for, like one that comes to mind is with electrical items that, it's not going to give anybody a shock, or the level of energy in it is low enough so that can't happen. So, and there's also I think there's a pressure directive. Those would be kind of the two most common ones. With thermocouples, there really is not a whole lot of documentation that goes with them. There's a standard that would drive a document, basically a kind of verification document that would say that the thermocouple has been tested and found to be one of the, the basic types of thermocouples. These different types are just, they have a different temperature voltage relationship and temperature capability. So the verification document would just say, yes, it's a type K, and it falls within this whatever error tolerance band, whether it's a special limits or standard limits. And those are actually the base thermocouples. You can see here, like the type T and the type E are the more accurate of the four basic types of thermocouples. And so again, that verification document will just say, yes, it's the type T, and it's special limits of error, for example. And a test, I know we do it at 100 degrees C just because it's a real convenient point. You may see other temperature points used. And now there are some thermocouple standards, and they will be tested at several different temperatures, and you'll get a little different kind of a document with that, a calibration certificate, much like what we looked at previously. And Jeff, you'll have to jump in if we have another poll coming up. I don't quite remember.
Yep, the next one is going to be in thermocouples. A couple slides yet, but I did want to remind everyone, as long as we get a little break here, if you do have any questions or comments, do go ahead and type them into the chat box or the Q&A section, and we'll look to get to those. And I did want to address one of our attendees. Made mention, and so we want to be sure to share that, is we mentioned NAVLAP and A2LA as some accrediting bodies. There are many other accrediting bodies such as IAS and many others, so we didn't mean to, we just mentioned two common ones that tend to be around as an example. There are many other accredited laboratories out there that, that are accredited by other bodies. So that's a good comment. We appreciate that.
Okay. So next I wanted to kind of move on to the sanitary probes, and these have a little different documentation requirements frequently. So we have the first one would be surface finish, and we see lots of needs for this, especially in pharmaceutical and the food beverage areas. So an example of this one would be, this kind of a mechanical surface finish, electropolish. And again, this is just kind of a real basic cert where you have the part number, maybe a customer purchase order number would be associated with it, and again, the person who prepared the report, up here the actual finish that was put on the part, and a tag number. And the other item that you will see a lot of is this material test report, where it defines the different metals that are within that particular material that the part was made out of, and what the quantity was of each one. There'll also be a heat number associated with that, and the part will be marked with that document. So this is a sample of that certificate here. It looks real similar to the other one. We also have the actual materials, the actual, right from the metal supplier, and they test all of these components. So we've got carbon, manganese, and all the other silicon, chromium, all the different components that go into making up, and in this case it's 316L material up here where it's defined. And they do some mechanical tests to it, be hardness, things like that. So that's what's included on a material cert. And then you'll also see the heat numbers in most cases actually etched or somehow labeled right on the actual component. Other approvals or things that you may see with sanitary probes would be this 3A marking. The part will actually be labeled with this symbol, and this is a not-for-profit organization, and they actually audit manufacturers. I don't know if it's annually or every couple years, but they do show up and they do audit to make sure that you're producing the parts that meet their standards for hygienic equipment. And then ASME BPE, which is the biopharmaceutical processing equipment. About the only thing you'll see there is a statement in some of the manufacturer documentation that they follow all of these standards when they produce their parts.
Okay, and before Bill launches into here Thermowell testing and documentation, we just kind of wanted to do another quick poll, just so we could see kind of, for those of you that are using Thermowells, what kind of documentation you're typically looking for. So what we'll do here is have this poll open for 30 seconds or so, and if you just want to indicate what testing and documentation you normally request, and you can choose more than one. We'll leave it open here for a few seconds. And again, just a reminder, if you do have any questions, go ahead and type them into the chat or the Q&A section, and we'll work hard to go ahead and get those answered for you just as quickly as possible. So it looks like we've folks are finishing up, so we'll go ahead and close this poll, and you got about 20 seconds here to go ahead and confirm your answers, and then we'll go ahead and pop it up so everybody can see what it is. And so far, it looks like pretty even as far as what people are looking for. Well, there we have it. Yeah, it's
Okay.
well, pretty equal across the board in the first 4 or 5. So.
Okay. Yeah. Yeah. I guess I'm surprised at the positive material identification. Yeah. Well, so we'll take a look at that too in just a little bit here. Thermowells do have probably the most testing and documents available of any of the components we've talked about so far. There's a lot that go into it, and one of the most important ones first is the wake frequency and strength calculation. So I'm going to spend some time talking about that and how we balance the immersion length of the probe, which is kind of the main governing factor in the strength, against the required immersion length to get a good accurate temperature measurement. So first, when we have a Thermowell stuck in a flow, we get these little vortices that form downstream, and this frequency of these vortices, if it matches the resonant frequency of the Thermowell is going to start to vibrate, the temperature probe is going to fail, and then eventually the Thermowell will fail. Either will break or it will crack and start leaking. And so we really need to be aware of that phenomena. Some of the manufacturers, this one happens to be from Alloy Engineering, they publish a little table with some conservative values that will give you kind of a rough ballpark idea of what an acceptable fluid velocity is based on the immersion length. So we've got the immersion length up here. If we look at 4.5 inches, and let's say we've got a 316 stainless well, it's showing 197 feet per second fluid velocity. And I think the ones in parentheses here are, actually 197 is probably steam and this is fluid, I don't quite remember. But anyway, the manufacturers will publish tables like this just to give you a little bit of an idea. Some manufacturers actually publish and provide the equations that are used to make these calculations, and that's pretty handy. They'll have these on their websites or wherever where you can go in and plug in all the variables and find out if the well is designed correctly for that application. If we don't do it right, we get what is shown here is a little stress crack, and this one's showing up with a dye penetrant testing. That would be another test that can be done to a Thermowell, and the document that goes with that. So we have the immersion length required to get a good accurate temperature measurement can be one thing, and then the immersion length necessary to pass those strength and wake frequency calculations can be another completely different number. If we look down on this graph, this one is, the error here is the percentage of the delta T, so it's a percentage of the ambient conditions against the fluid temperature that you're measuring. And this one was done at 3 different temperatures, so it was done in ice, 100 degrees C, and 200 degrees C, and with a tapered Thermowell, which is shown in the photo here. So if we look down on the immersion length, we can see right about this, 2.5, 3 inches of immersion. Most of that error has gone away. If we use something shorter than 2 inches, we have some fairly large errors here. And if we get out to 4 inches and greater, the error is pretty much completely gone. And this is all due to the heat transferring from the external components of the temperature probe and the lead wires that lead down to the sensing element, which is at the very tip down here. And so if you have a hot process and a cool ambient conditions, it's going to be affected by some of that, have a little bit of a cooling effect on it by the ambient conditions. One of the ways that we can get around not having enough immersion but still passing the wake frequency and strength calculations is to do a little something to the well to disrupt that flow. And you've seen some smokestacks out in industrial areas. They got this little spiral wrap around them. Well, what they're trying to do is to disturb the wind flow around that so we don't get this wake frequency issue and cause that smokestack to vibrate. Thermowell is the same way, so we can use a twisted bar stock, for example, and this would be, probably drilled out for the temperature probe. I know of at least one manufacturer that offers these now. And it seems like a fairly good idea for those situations where you need more immersion length, but you do have a wake frequency issue with a cylindrical thermowell. So the information that you would need to supply for this would be kind of supplied in different formats. I don't know if we can read this very well, but the bulk of the form here is just the dimensions of the thermowell, and the end user would need to supply things like the properties of the fluid, the temperature it's at, the velocity of that fluid, the pressure, and viscosity. Although if we know what the fluid is, a lot of times we can look up and find out what the viscosity of that fluid is. So, but this is a kind of a form that you might be asked to fill out, and typically the items that you would need to fill out would be highlighted in some fashion. Send that back to the manufacturer, and they can go ahead and run the calculations, and then they'll develop a form that says, based on this set of conditions, your thermowell either passed or it did not pass. And if it didn't pass, they'll make some recommendations as to how that thermowell design can be changed so that it does pass. Some of the other testing that can be done with thermowells and certifications, there's this NACE, which is a kind of a corrosion authority, Canadian registration number. In Canada, they it's just a way to track things that are used in pressure vessels over 15 psi. So there's hydrostatic tests. Again, we talked about electropolish and mechanical finishes. One of the other ones would be the certification that no polishing compound would be used, and that has to do with the possibility of some materials that may contain just some
usually animal derivatives,
kind of pathogens or whatever that might be within that actual polishing material. A lot of them is derived from animal parts, so that can be a problem. I guess the one that comes to mind is this mad cow disease and kind of a deal. So in our poll, I saw where people had selected this positive material identification. So this uses X-ray fluorescence to identify the materials in the well. And so we can actually take a thermal well, and it's been manufactured. We have the heat numbers. We have the material certification that tells all the components and everything. And so this is kind of the belt and suspenders look at that, so we can actually use this device to verify that, yes, in fact, based on this test, that this really is 316L material, for example. We see this a lot of times on some of the more exotic materials where, corrosion and having a failure due to corrosion would be a significant event. So regular X-rays can be used to show potential cracks within a thermal well, or to ensure that a weld has been made with 100% penetration. And then down on the very bottom of the list here, even some companies have their own tests that need to be done to Thermowells. I know Exxon has one that has some pretty stringent requirements, and they're laid out in their own specification document. We get to Europe, they have some other like an inspection certificate that is required many times. We also see some other things where you want to control the sulfur content, the ferrite content within the material. We actually see this in the U.S. also, but a lot of it is a European requirement also. And this pressure equipment directive, if the Thermowell is going to be used in anything above a certain pressure, it needs to meet that directive. And with that, I think we're getting to the end here, and I just wanted to throw out a couple of things here. There are just dozens of tests that can be done to RTDs, thermocouples, and thermowells, and we just looked at some of the most common ones. And if you need something in addition, don't hesitate to ask, because chances are manufacturers are going to have something in place to take care of that. And some of the niceties that you may want to look for is, since this stuff always gets lost, we end up with a lot of calls where, the parts are shipped with the documentation and mysteriously the documentation disappears. And as a lot of you, I'm sure, know, without documentation, the parts aren't much good. So if that's available online, or some kind of cloud storage, whatever, so that you can go back and retrieve it quickly and easily while the third-party watchdog is staring over your shoulder, that's always a good thing. So, and with that, I'll turn it back to Jeff.
Yeah, so just again, if you do have any questions, we've got a few minutes left, so go ahead and type them into the chat or the Q&A section, and we'll try to get you an answer for those. And also wanted to just find out a little bit more about you folks, so I got another quick poll, which we'll open up here, and really just want to learn a little bit more about your primary industry and kind of your needs from a sensor thermowell testing and documentation. It always helps us to kind of get a good idea of the cross section of the attendees. So appreciate you giving us a little bit of information there. And again, I know, Bill, there's at least one or two questions, so I'll get those shortly here. Well,
yeah, if anybody has any other questions later on that you think of, don't hesitate to give me a call or shoot me an email. Be glad to help you out. So.
And there's about 20 seconds left here in this poll, and we'll go ahead and post it so folks can see who all has attended. And as Bill mentioned, there are literally hundreds and maybe thousands of different combinations of tests and documentation that can be supplied. So if you need something and you're not getting it, go ahead and ask about it. So good. Well, it looks like we've got majority are biotech, pharma, and chemical, petroleum. And if it's not important, it's critical. So that looks like that makes up 100%. So as we like to say, the documentation is part of the product. It's not something that's an add-on, because without it, as Bill said, there's not a lot that you can do with it. So let's go ahead and take a look at some questions here. As far as there is a question here regarding the presentation, yes, the presentation will be posted on our YouTube site or YouTube channel, yeah. And so
I'll have that up. Probably tomorrow, later in the day. It takes a while to upload it, so yep. Probably.
And then what we will do is we can send out an email to everyone when it's loaded with a link right to the YouTube channel. So so if you miss something, don't worry about it. You can see that. And I think we had a question here. about, looks like a skin tube thermocouple and RTD, and how a transmitter would be connected to thin film elements.
Oh, you know, actually, yeah, this is probably for, I'm guessing, on a some kind of maybe a steam tube or something, boiler tube. Yeah, a lot of times those are welded on to those tubes. I've seen some clamping type things also. And the transmitter, of course, probably has to be mounted remotely from that location because they're usually fairly warm. So it should be actually pretty straightforward. If you wanted to send me an email later, I can send you some more information on that.
Okay. Let me check real quickly, see if we have any other questions. Doesn't look like we do, but do want to thank everybody for attending. If you do think of a question or you come up with an issue in the future, feel free to shoot us an email or give us a call. And we do have our next RTDology session will be in September, and that is on temperature sensor calibration and verification on September 12th. And look forward to seeing you there. And in the meantime, have a great summer.